Thank you, Danielle. Good morning, everybody, and thank you for joining us for one in a series of Dynamics webinars. My name is Ron Beck, Head of Engineering Product Marketing here at Aspen Technology. I have a very small role to play today, which is just to introduce the webinar. So I'd just like to mention that we've accelerated our schedule of Dynamics webinars. We've found that over the past 6 months, dynamic modeling has been one of the fastest growing areas of interest among our engineering products, so we've added several new webinars to the series. We hope you will enjoy this one and give us some feedback as to future topics you'd like. One of the areas that customers have told us they're most interested in modeling with dynamics is columns, and so that's what we're going to be discussing today. The two presenters who will cover the topic for you are the marketing manager for dynamic simulation, Nick Brownrigg, and the product director for dynamic modeling and simulation, Ajay Lachwanan. So without any more delay, I'll turn it over to Nick to start things off. Go ahead, Nick.
Thanks, Ron. As Ron said, I'm Nick Brownrigg. I'm the marketing manager for Dynamics here at Aspen Technology, and I will be moderating the webinar today. We have an ongoing series of webinars that we host, and a number of them will include Aspen HYSYS Dynamics and Dynamics in general from Aspen, including a webinar coming up on Thursday, which will showcase our new pressure safety valve sizing feature included with Aspen HYSYS Dynamics. So that will cover using Aspen HYSYS Dynamics with that feature. The webinar that you'll see today covers a few of our solution areas that we offer, including conceptual engineering and safety analysis. And I would like to remind you that to help our users get started with Aspen HYSYS Dynamics, we have a wealth of materials online, including a jumpstart guide that refers specifically to using dynamics with columns related to this webinar very closely. And that jumpstart guide also includes sample models that the user can open up directly in Aspen HYSYS and begin using Aspen HYSYS Dynamics on. And again, those are available on the Aspen Tech website under the Aspen HYSYS Dynamics page. With that said, I would like to introduce our main presenter, Ajay Lachwanan, who will give you a short overview of using Aspen HYSYS Dynamics with columns and then a demonstration. Take it away, Ajay.
Thank you, Nick. So in today's webinar, in the next 30 minutes or so, we'll look at an overview of the HYSYS Dynamics V8 user interface changes in V8 and version 8. I'm going to focus just on the user interface. As Nick mentioned, there are multiple webinars on Dynamics that are coming soon. One on Thursday on pressure safety valves, on how to rate them in HYSYS Dynamics. There are new column models that have been added as part of the acid gas project. So you'll hear about all of these in multiple webinars. So in this overview, I'll just cover the user interface. We'll also then go into the details of dynamic modeling of distillation columns, look at benefits, how to transition from steady state to dynamics. This is usually the stumbling block for most of us, so I'll cover that first. We'll then look at control schemes, followed by a demonstration of how you could test the various control schemes, and look at how an upset would propagate through a column. In this specific case, I'll be looking at seed upset. We'll then look at modeling suggestions, followed by customer examples, wrap-up, and Q&A. Many of you may have already seen the new interface by this time. With the new interface in Aspen HYSYS Dynamics in version 8, we have a dedicated Dynamics ribbon, which is workflow-oriented. So the very first button is to switch into Dynamics mode. There is a Dynamics assistant that will help you set up the model, transition it from a steady-state model to a Dynamics model, It will also, you can also, by default, it will also run every time you try to run the model in dynamics mode. It's just a checklist. You should use it as such, as a checklist. And depending upon your modeling requirements, you may choose to take its suggestions or ignore its suggestions. You'll see during today's demo that I will be ignoring some of those suggestions because I've set up my model differently, the way I want to do so. Then there's the integrator settings. There's, the runtime buttons that are required. There are several modeling options, all of which bring you into tools that are required for dynamics modeling, the control manager, faceplates, etc. The nice thing about the new user interface is that the flow sheet is actually a wallpaper. So while you simultaneously observe strip charts, faceplates, and how the dynamic simulation is proceeding, you can also observe mass flows in your flow sheet. You can look at temperatures, pressures, whatever you're interested in. In today's demonstration, I'll show you, you'll see how I'll be looking at the mass flows through this particular column model, while still looking at the faceplates and the strip charts that show the actual dynamic simulation. Another small change, which is nice, all of the dynamic utilities in the model palette have been grouped together. So you'll see the controllers and various other utilities in there. There are also several column types, all of which have been grouped together under a column tab, about 14 of them, almost all of which can be used in the dynamics mode. Again, as I mentioned at the beginning, there are numerous other changes, new column types, as well as pressure safety valve related updates, all of which you will hear about in upcoming webinars. Let's now dive into dynamic modeling of distillation columns. But before I talk to you for 30 minutes, I'd like to get your feedback. I'd like to run a short poll question. I'd like to know from you, what problems are you trying to solve with dynamic modeling? Is it compressor surge control, distillation column control, design and analysis of depressurization, overpressure protection, and flare systems, design and analysis of startup, shutdown, process transition strategies, safety and hazard studies, operator training, and DCS checkout? This is a multiple choice question. Please choose as many as you feel appropriate. We'll run this for about a couple of minutes. So please take. And the time limit has been set to 5. So we do have a couple. We'll wait. We'll go for about 3 minutes or so. Okay, so I'm going to go ahead and continue with the presentation, just so there's not a delay in the webinar. So while you are answering the poll question, what are the benefits of dynamic modeling of columns? Most of these benefits are general to dynamic modeling, but one of the key benefits is efficiently design the process and control system simultaneously. You can develop, evaluate, and test control scenarios. We'll see some of that in today's demonstration, and tune control loops. You can improve the operability of your column. Specifically, if you'd like to study how upsets propagate through your process. Today we'll look at how feed upsets will propagate through a column. Startup, shutdown, process transition studies, and if you do have highly heat integrated processes, you definitely want to model that process in dynamic mode. You can also increase safety and reduce hazard around pressure relief. Again, there's a webinar on Thursday on that, as well as emergency shutdown.
So, Ajay, we have the answers to the poll, if you'd like to have them.
Oh, great. Yes, Ron.
So, thank you very much. Almost everybody took the time to answer the poll. and I'll just let you know what areas of interest people have. I'll read them off, and maybe you can make a couple comments if you want, Jay, but I'll read them in order. So compressor surge analysis, 29% of the people on the webinar were interested in or working on. Distillation columns, 48%. Design and analyze, what was this question?
Pressurization.
Depressurization, that's 49%. Startup and shutdown, 44%. Safety and hazard analysis, again, about 25%. And operator training, about 10%.
Okay.
So that's pretty interesting answer. Remember, people could get more than one.
Yes. Thank you, Ron. That's good feedback. Thanks to all of you for responding to the question. So, again, one of the first is to almost, in most cases, in 90% of the cases, we already have a steady-state version of the model, and we need to transition that to dynamics. So I'm going to go through that first, and then switch over to dynamic mode and have a demonstration. So what are the key things? There are 4 to 5 key steps that we'll be outlining today. The first is the boundary streams. So if you have your steady-state simulation, you want to insert valves on feeds and products, append new streams, and specify pressures. I'm going to go ahead and do that while I look at this, while we go through that. As mentioned earlier, here what I have is a simple debutanizer column. I have 2 feeds going into that debutanizer column. Feed 1 is less rich in butane, and feed 2 is very rich in butane. All of the butanes are taken off at the top, and C5 plus stream comes out the bottom. So in order to transition this model, I've already added my valves on the feed. I'm going to use the dynamics assistant to lead me through the transition. I'm going to run the dynamics assistant, and as expected, it tells me some of the same steps to transition it. First, append new valves and streams, disable stream pressure specifications, etc. I'm going to first do the appending of new valves and streams. Again, as I said, what this uses is a set of default rules. So I encourage all of you to look at a suggestion, choose the ones that are appropriate for your specific model. In this particular case, for my model, I do not want to add a valve and a controller on the vent stream. I'm going to set it to a minuscule value, very close to 0, and just set that flow rate. So I'm going to request the dynamics assistant to add a valve on my butane stream as well as on my C5 stream. So I'm going to go back, make sure nothing else is checked. I'm going to say make changes. And as you could see there, it added the valve. It also set the pressure specs on my outlet streams. Now, in this particular flow sheet, the color scheme I'm using is the dynamics pressure flow spec. Blue, a stream in blue means that no specification has been made in dynamics. A stream in yellow means that a mole of flow specification has been made in the dynamics tab. Feed 2, for example, is really bad. It has both a pressure specification and a mass flow specification. And green means that, which is what we're trying to get to on the boundary streams, means that there is a pressure specification set on the dynamics tab. Remember, this is a pressure flow dynamic simulation. So that's my first step. It went ahead and appended valves. The next step was related to specifying pressures, flows, etc. Again, the dynamics assistant is telling me to make those changes. I'm going to ignore the append new valves because I don't want to append a valve on the vent. The disable stream specifications, disable stream flow specifications, and enable stream pressure specifications. Let me just take a look at what it is trying to tell me. It wants to remove pressure specifications on feed 2. As we said, red is bad, and we want to remove that spec. It wants to add a pressure specification on 2 feed 1 and 2 feed 2, the boundary streams. Yes, I do want to do that. It also wants to disable stream flow specifications. Let me just take a look at what it wants to do here. go to the flow specs tab. It wants to remove flow specifications on feed 1 and feed 2. Yes, I want to do that. So I've reviewed all the 3 changes, and I'm going to go ahead and make those changes. So at this point, I've got green color on all of my boundary streams. So my boundary streams are set up correctly. And the valves have also been, the pressure flow relationships are automatically turned on, so I don't have to worry about that. So let me go to my next step, which would be to set dynamic specifications. We need to set the dynamic specification. Again, you could add valves, controllers if you wish to do so on reflux streams and the vents, etc. But in this particular, for this demonstration, I'm just going to set the flow of the reflux and the vent. And we need to ensure that the valves have a pressure flow relationship. So going back to my demonstration here, okay, so I'm going to reanalyze again. It's telling me to enable an internal stream flow specification. That is my reflux flow. Let me double check. I'm going to go ahead and uncheck the other 2. As you see, I only use this as an assistant. I check everything that it suggests. It wants to set a flow on my reflux, and I'm going to go ahead and make changes. So at this point, we've pretty much made all the changes that we want. On the vent stream, I'm going to enable a flow spec on my dynamics tab. Again, I'm going to set it to a minuscule value. And so it turns out in yellow, but that's by design. I want to do that for my demonstration. Next, we'll have to size the equipment. Anytime you want to run a dynamic simulation, ensure that all of your equipment is sized appropriately. The condensers, reboilers, trays, in this particular case. I'm going to go ahead and in my column environment, in the dynamics mode, I'm going to go ahead and set the volumes for the condenser and the reboiler. I'm going to use about 530 feet cubed for my condenser and reboiler for this particular demonstration. Again, you will have values for these. So I'm going to set that. And I'm going to enter the column environment, go into the rating tab, and specify the tray space, the diameter, the veer height, and the veer length. The tray diameter, I'm going to say, is 4.5 feet. The tray spacing, I'm going to say, is 1.8 feet. Again, these, depending upon your particular model and simulation, you would have your own numbers. There are also utilities, which I will point out in a minute, that you can use to quickly size your trays and columns. So veer length are about 4 feet. So at this time, I've completed my sizing. We've set our internal specs, and we've set our vent flow on top. So we're almost ready to run in dynamics. The next step is to add controllers and strip charts. To add a controller, you first have to pick a control scheme that we'd like to use. For today's demonstration, so before I go into what I've picked for today's demonstration, let's just look at a simple distillation column. One feed, a reboiler, and a condenser. Right? There are 3 inventories, as we saw. There's the column, the reflux tank, and the reboiler, all of which need to be sliced. There are 5 manipulated variables, which are the feed flow, the reflux flow, the boil-up flow, the distillate flow, and the bottoms flow. And there are 5 controlled variables, which are the level in the reboiler, in the reflux drum, in the column, and the top and bottom purity. So even for a simple distillation column, it results in a 5x5 system. For more complicated columns, you will have a larger system, and hence you can have many control schemes. The specific control scheme that I'll use in today's demonstration is commonly referred to as an energy balance configuration, or also known as an indirect feed split strategy. In this strategy, the product flows, the distillate and bottoms flow, are controlled by the level controllers on the reboiler and the condenser. and this in turn controls the material balance within the column. The product composition is controlled using a temperature controller which manipulates one of the stage temperatures within the column. Again, how do we pick that stage to manipulate? Which one should we manipulate? There are many ways in which you could do this. I'm just going to say, you could do a case study, run through various cases, and then choose the stage that responds well to changes in reboiler duty, etc. Or you could use rules of thumb. In this particular case, I'm just going to look at the column profile. I'll look at a plot of temperature versus temperature on each stage. As you can see, the temperature is changing reasonably significantly between trays. There is a feed coming in on stage 4 and another feed coming in on stage 8. So we could pretty much choose any of the stages in between those two. I'm going to choose stage 6 in today's demonstration. Again, I'm just using a rule of thumb. You could do a case study and then choose the appropriate stage that you want to control. So for the temperature controller, I'm going to control the stage 6 temperature. The secondary composition control is done by setting the reflux flow that I already did as part of my setup. And the pressure control on the condenser is done by manipulating the condenser duty. So I'm just going to walk you through setting up one of the controllers. For the other controllers, I'm going to open up a fully specified model so that I don't hold all of you up with setting up each of these controllers. So I'm going to set up the temperature controller. I'll use a PID controller for this, and let me choose. I'm going to choose my stage temperature. So I'm going to choose stage 6 temperature as mentioned earlier, and select my OP. I'm going to select my reboiler duty. I've done that. Now I need to also select, as you know, when you have a controller, you need to select the PV minimum, PV max. In this particular case, when we looked at the charts, it was around 103 or so, something like that. So I'm going to say 98 Celsius, and let it go up to 126 or so. Tuning, controller tuning. This is something that we could have a separate session on itself. But for this particular demonstration, I'm just going to use some default values, 2 for the gain, 5 for the integral reset. And yet, it's not fully solved at this point. So we do need to go into the control valve. We see that the steady state value is about 3.4 E6. So I'm going to set that to the minimum to be a very small value, and the max to be about double the steady state value, and there. So now the temperature controller is fully specified. Again, the tuning you'll have to play with. I'm using a default tuning for this particular demonstration. So you can go ahead and continue doing this, and as you can see, I've done that, and I've got all of the controllers set up for this particular energy balance configuration control. As mentioned earlier, we've got the flow sheet as a background or a wallpaper. We also have various trip charts. The first trip chart shows the feed flows. I'd like to study this